Alright, so let's go over the package that I sent to you guys, problem number 22. So we have a pulley. Oops. Then the pulley is like this. And there's a ball in there. There's a mass in here. And then it's so good that so the masses are 2.9 kilograms and 7.6 kilograms. Have both connected by light string, passes over frictionless pulley right there, and then you have to calculate the magnitude of acceleration, tension, and so on, so on, so on. So again, let's assume that one of them is the most massive one, this guy over here. So this has a mass of 7.6 kilograms. So what you do in problems like that, you isolate your system, and then you ask which forces act on it, and you come up with your gravity. 7.6 kilograms times 9.8 meters square second. Okay, and you also have tension force in the air. So those are the only two forces. Ignore air resistance. It's not part of your free body diagram, but I like to indicate there is an acceleration. Why? Well, this is your experience, right? So there is an imbalance of forces. So the heavier one will tend to pull the other mass up, and the system will circulate, will move with some acceleration. So I put it right there. So when you do your Newton's second law of motion, sum of forces in the y direction must be equal to mass times the acceleration in there. Then you go 7.6 kilograms times 9.8 meters per square second. That is the weight minus your tension is equal to the mass, 7.6 kilograms times acceleration. So we have one equation. Oops, sorry. Have one equation and two unknowns, which is t and a. We don't know this value. So what we do? We take advantage of the other material in there, and then we do the same thing. We do our free body diagram. So free body diagram, we do have mass for this fellow mass, which is equal to the weight of it, 2.9 times 9.8 meters per square second, and then it has a tension. And if we are assuming this rope or string is massless, and there are no dissipations in the pulley, the tension is the same. So the value, the magnitude of the tension force is the same. So in this case, and because this mass here is driving the system down, which means it's pulling this guy up, what I will do, I will do my free body diagram, which I already did, but my Newton's second law of motion in it, I will do so that the tension carries a positive weight, so T minus 2.9 kilograms times 9.8 meters per square second. So that's the imbalance of forces is equal to that mass, 2.9 kilograms times acceleration. So again, I got myself a second equation, which will remind you or remind us the problem that I did in the second lab yesterday, in which we get two equations with two unknowns. So what do we do next? We take the tension here, we plug it in there, and then we can find the value of acceleration. And once you have acceleration, you plug back in one of these equations to get your tension. To find out how long each of this mass move, this is subject of chapter 2 or 3. So we have an acceleration which we are supposed to calculate. I don't know what the value. I'm just going to copy from the solutions. Supposed to be 4.39 meters per square second. So we calculate the acceleration if that's the right value. I didn't check, so you check. And then to find the displacement, we can use Bernoulli, right? Oh no, we want to find displacement. We know acceleration, we know the time. Both objects, oh, in the first second. So time is given. So we want to find how long they move in the first second. So we have the time, we have acceleration. We can use y is equal y naught plus v naught t plus half acceleration times square. Okay, and then we plug 1 second here. We can have our displacement, which is y minus y naught. Okay, that is problem number 22. Let's see anything good here. Problem 21. Let's go to problem number 21. So you have a car, right? That's pulling a trailer. Oops. Car is pulling a trailer. That's the car. And that's the trailer. Oops. What did they do? There you go. There you go. Trailer should have a wheel. Okay. Car is pulling a trailer. Oh, the trailer is only 275 kilograms. That's the mass of trailer, and car is 1.110 kilograms. Okay. Together, the car and trailer have acceleration. So acceleration is given. Okay. 2.00 meters per square second. The positive x direction. Very good. So write down that information. In neglecting frictional force, woo, that's great. No friction and no air resistance. Determine the following. The net force on the car. Well, the net force on the car. So we isolate the car. So the net force on the car is the one driving, so it has a thrust which is due to its engine, right? It's burning gasoline. I'm gonna call this force of car. So essentially what it does, the car's will exert a force on Earth, that direction. So this is car on Earth, but when we do a free body diagram, we want the force that everybody else in the universe do on the studied object. So it's the car. So this force car, in fact, is force Earth on the car. Okay, so keep that in mind. But also the car is attached to the trailer, so there is some backward force here. Can I call force of trailer on the car? You also could call tension because there is a cord there. And there is of course a normal force because the car is on the floor, and there is the weight of the car, right? I'm dropping the units here. But this is the free body diagram, and the net force would be F of car minus F of trailer. This is the net force, and that's what we want to find. But here's the problem. I don't know this, I don't know that, I'm in the middle of a banana. How can I solve for that? Well, but remember, the problem tells us the acceleration. And remember that I mentioned in class, when you have problems with connections, with the trains carrying a caboose and there is another train, or when there is thing connected, sometimes it's a good thing if you make the whole system just one thing. Okay, so if you have just one thing to think of, then the net force the net force the net force is going to be equal, because see, the normal cancels with gravity. So the net force, according to Newton's second law, so the net force is equal total mass times acceleration, and we have the total mass. So the total mass is this much plus this much, so it's 1,385 times acceleration is 2. So we have the net force, and then we can say, hey, you know, the force on the car is equal that number 1,385 times 2 plus Ft, right? We are almost there, but I don't know Ft. So what we do? Well, we now isolate this guy down here. So if you take the trailer out and isolate it, we have the weight of the trailer, we have the normal force on the trailer, remember there is no friction, and there is the reaction to that Ft that I was considering here. So we have the reaction that has the same magnitude, and here when you apply Newton's second law of motion, Ft is equal mass of trailer 275 times acceleration. So then acceleration we know, piece of cake. So we found this, plug in here, in there, and we have the force on the car. So we found the force of that force on the car is the net force on the car is F car minus sorry, I think I messed up. So let me start all over. Car, mess up in the net force. Sorry about that. Okay, so here it is. We have a car, have a trailer. The car is 110 kilo. Oops, 3 ones, 0 kilogram, and we have a trailer that is 275. I'm not gonna put the units here, and the car itself, if you isolate the car, there is the force of earth on the car, let's call F car, and there is the force of trailer pulling it back, right? So the net force on the car, the net force on the car is equal to F of the car, the thrust, minus Ft, and this is equal to mass of car times acceleration. So the net force on the car is equal to 1110 times acceleration 2 Newton. Okay. Remember, we do have weight, we do have normal, but they cancel out. right? So the net, there is an acceleration, don't forget. So the net is going to be the pulling force, which is driven by the engine, minus um, the tension force, or the force the wagon, the trailer exert on the car by retarding its motion. So, and the net force is equal mass of the object you're studying times acceleration. Okay. Now, if you look at the trailer itself has also weight, it's also normal force, they cancel out, right? And has an Ft. I'm calling the same symbol, but they are different forces because the direction is different. See that? The direction is not the same. So that's it. So for the trailer, Ft is equal mass of the trailer times acceleration, which is 2. And then we can solve that. Okay. And this is also the force the trailer exerts on the car. So the net force on the trailer is equal to this. And the force the trailer exerts on the car is this much here. The magnitude of it. The force the trailer exerts on the car, which is this one, is going to be the negative of this one, right? So pay attention to that. And the resultant force exerted by the car on the road. What is the resultant force exerted by the car on the road? So what are the forces the car exerts on the road? Well, the car pulls the road in that direction. And that's why the road itself does this. Okay. So the resultant force is going to be given by what? Well, the car pulls the road in that direction with a force that is equal to Ft. Did we calculate Ft? No, Fk, F the car. F car is equal 11102 plus Ft, and Ft is what, 550, right? So this is equal 1, no, 2, 2, 2, 0 plus 5, 5, 0. So Fc, force earth exert on the car, is equal to 2, 7, no, 2, 7, sorry. Two seven seven zero newtons, right? So that's it, 277 newtons, but also has a normal force. No, I'm sorry. The car exerts a downward force on the road. So on the road, the car exerts a downward force, which is equal to, or the pair action reaction of the normal force, which is equal to its mass, 1110 times 9.8. So that's the weight. So what is going to be the resultant force exerted by the car on the road? It's going to be this downward force and sum with this one. That's it. So you have to take the square root of this square plus this square. So the resultant, the magnitude of it, is going to be square root of 2770 square plus 1110 times 9.8 square. Okay. So we have to include the normal, and we have to include the reaction to the normal, and to the reaction to the pull forward force. Then the angle is going to be tangent of this much, which is the reaction of normal, divided by this, which is the is the car on the floor. Okay. Let's take a look at problem number 20. I think I did for one of the labs. So we have a block here, M1, and go to a pulley, down, block M2. So M1 is 5.5 kilograms, and this M2 is 11.7 kilograms. And then how do we solve this problem? This is exactly the problem we had in the lab. You guys should learn this stuff. So we have an acceleration going down, and then what do? We isolate one of these bodies, weight, and I'm not putting the units here, minus the tension. Forget there is an acceleration down. It's not part of your free body diagram, but helps you to visualize what's going on. So for now, call this positive direction, makes our life easier. 1.7 times 9.8 minus t is equal 1.7 times acceleration. Found myself with one equation, two unknowns. Yeah, looks like the first problem I solved, remember? Now when you look at the mass 1 has weight, has normal, has tension, and I could complicate your life. Perhaps I would do that in the exam and say, hey, there is a kinetic friction in here, or static friction. Could do that, right? So the only thing, if there is friction, the only thing you do, you add some backward force here, right? But in this problem there is no friction, so you don't need to worry about it, right? You don't need to worry about this. Okay, so for block M1, the only thing that you can do to suffice Newton's first law of motion is that T is equal M1 times acceleration. Piece of cake, you got your tension, plug it in there, and then you can calculate acceleration. And once you calculate acceleration, you can solve for everything else in here. The problem number 17 is a similar or perhaps the same set of equations you might find if you attempt to do it. Not so much different from problem that you have a car pulling a trailer. The difference here is, see, the acceleration is given. It's the same thing. The acceleration is given. See if you can do that. The acceleration is given. The difference is the airplane has a propeller, right? Let's see. A glider is being pulled by an airplane. Yeah, the acceleration is given, and the airplane has a thrust by the airplane propellers. So it's kind of what we did in the car. It's exactly the same thing. You should be able to do it if you understood that problem of the car. So the airplane has a thrust, which is provided by its own engine that rotates the wheel. The wheel pull Earth opposite, in the direction opposite to that the airplane goes. Earth send the airplane forward. So that is the thrust. But also has a cable with a tension that pulls the airplane in the opposite direction. So thrust minus tension is equal mass of the airplane times acceleration. Okay, and for the glider, you do the same thing. You, in this case, we are ignoring rolling friction, and then the tension is equal to the mass of the glider times whatever acceleration they have. Okay. How about, I hope that never happens to you, but let's say you get in an accident, or you're playing soccer, or you fall from a tree and you ended up being a patient like the one in question number 15. So let's see how that happens. So if you are in the hospital, kind of with the legs up, all broken, at least you can, reason physics and remember this, your humble professor, and then have some fun time calculating things, calculating tensions and normal forces and all of that. I'm being serious. I'm not joking. So we have something like this, and we have a leg like that, right? That's a leg, and the leg is strapped right here, and it goes over a pulley and another pulley, I think. No, I have to go further. Sorry. Ooh, there you go. Another pulley right there, and then there is a third pulley here that forces this thing in there, and then it goes in here. It's another pulley, and then that's hold it to the wall, and then it falls. Looks complicated, huh? And this mass is pretty much 8 kilograms. Okay, so remember, if all these pulleys are super pulleys, oh, massless, no friction, no nothing. And if you look at this free body diagram for this hanging mass, right, and it's not moving. Hopefully, it's not moving. So the weight of this mass, remember, the weight is different from mass. 78.4. Yeah, 78.4 Newton. The weight equal to the tension, this tension here, right? But see, once you calculate the tension, which is, so since it's not moving, T minus W is equal to 0, so T is equal to W. So the tension here is the same that goes all over the place and down. Okay, so the tension that supports the leg is 78.4. Okay, right. So if you do a free body diagram for the leg, is a weight of leg, and there is a tension out, and this is 78.4. So I would imagine they would adjust the weight here, adjust the mass, in order to to balance out the leg, basically. And what is the traction force exerted on the leg? So in addition, we have a traction force here. See that? So if you take a leg, this part of the leg right there, so there is a force. So essentially, if you look at this pulley right here, what are the forces on the pulley? Well, the pulley has a tension T in that direction. It has a tension T in that direction, and the angle is given, isn't it? So we have an angle of 70 degrees. And and this pulley and the whole thing pull the leg with a traction to, and it's said to be horizontal, so let's go to the left that way. Okay, so that the pulley doesn't move. So we have these two forces. In fact, it's the same one: tension, tension, pulling to the right, and the leg itself that is attached to the pulley pulls the pulley to the left, and then the pulley itself is subjected to 1, 2, 3 forces. So you do our little table, remember that? X projection, Y projection, and then you are writing down the forces. We have, can I call this T? So I'm going to call this T1. It has the same value, but just to differentiate. And the other one is T2. You have T1, you have T2, and then we have T, the big traction. And the pulley is not moving, so the sum of these three forces as a vector should be equal to 0. Right? Hopefully there is no motion. My goodness, remember? So let's call this direction as positive. Can I change the color of my pen? I wonder if I can. Let me see. Should be able to get a color. Oh, perhaps here. Let me see. So then, oh, I do. Okay, that's one force, two forces, and three forces. Let me bring my axis. Cool, I like that. That's my positive x-axis. That's my positive y-axis. And then you ask the question, how does T1 project in x? Well, T1 is going to project in x as positive T cosine of 70, and positive T sine 70 is how it goes to the y direction. And how does T2 project in x? Well, as T, and 0 in y, positive T. And the traction in x goes negative traction, and in y is 0. So we just need to sum these terms. We know the tension, and then you can get your traction. Okay. The problem number 10 is a cool one too, and has lots of nice concepts. See how you do that. So you have a crate. The mass of crate is 33 kilograms. Okay. And it's on the bed of a truck attached by a cord to the back of the cab, as in the figure. The cord can withstand a maximum tension. So the maximum tension is equal to 53 newtons. Okay, 53 newtons before braking. Neglecting friction between the crate and truck bed, find the maximum acceleration the truck can have before the cord breaks. Well, it's a piece of cake if you do your FBD. How do we do an FBD? Let me change the color and just explore. Cool. So you take a box, right? And then what are the forces? Well, I have the weight, I have the normal, they cancel out, so they will not help me to solve what's going on in the x direction. And there is, of course, the tension that is holding the crate in place. But see, it is said there is no friction, right? It said there is no friction between the crate and the truck. So let's do the two situations, one with friction and another one without friction. So if this is the case, so when you do your free body diagram, there is an acceleration to the right. The tension is the only force in the x direction, so Newton's second law, T is equal ma. So since the maximum force or the maximum tension allowed is 53, we can readily calculate our acceleration. Okay, acceleration can be solved, no problem. I don't like this color. How about this one? Okay, but let's assume you have a situation, and which is quite common, that you have just the crate in there, okay, and there is friction, and the friction is static, and so of course you have static friction with a coefficient of static friction, and you also have kinetic friction with a coefficient of kinetic friction. So let's say the coefficients are given. Static is 0.5 and kinetic is 0.4. Usually kinetic is a little bit less than that. Okay. And then the truck is moving to the right with an acceleration given. Let's say the acceleration is 2 meters per second. I'm just making up a number here so I can calculate right there. Okay. So let's say the truck is going with 2 meters per square second, and my question is, I ask you out of the blue, do you think the crate, at what velocity the crate, let's say I ask you, here's my question, will the crate stay in place, or you move around on the truck bed? So what do you think? How would you calculate that? No problem. You do your free body diagram and then say, okay, the truck goes to the right. The crate exerts a force on the truck to the left hand side. The truck exerts a force on the crate forward, and that is the static friction. Let's assume this static friction. Okay. What is the maximum value of a static friction? Well, the maximum value of static friction is equal to the coefficient of static friction times normal. In this case, normal is mg. So then you go 0.5s. This is maximum, right? The maximum value. 0.5 times mass, which is 33, times acceleration 2. Okay, this is the maximum force the static friction can handle. That's the maximum, okay, Newton. Well, but according also to Newton's second law, this should be equal to the mass of the truck. No, wait a second, this is not 2. mg. According to Newton's second law, the static friction, the net force, is equal to mass times acceleration. Times acceleration, which is 66 newtons. So if the crate moves, if the truck in fact moves with an acceleration of 2 meters per square second, which means the crate is also going that direction, according to Newton's second law, this static friction has a value of 66 newtons. What is the maximum value of static friction under these conditions? Is this number here. Let me calculate that. So when we calculate, the maximum static friction is 162, which is bigger than 66. So since the maximum static friction is bigger than the actual force that pulls the crate forward, and that is the friction, then it's safe. The crate's going to stay in place. But see, if the acceleration were not 2, but let's say if it were 5, if it were 5, what would happen? Well, now it's going to be this much, 165 newtons, bigger than that one. So with an acceleration of 5 meters per square second, your crate is going to start sliding. If you don't understand, email me. Have a great weekend.